Right, let's look at the metrics for this whole sprawling mess. The project is comprised of 35 files totaling 157 1 kilobytes of extracted text. The status breakdown shows 32 included files and 2 duplicates, which is standard practice for a project that clearly hasn't learned to clean up its own dependencies. When you look at the language breakdown, Python dominates with 2062 lines of code, while JavaScript accounts for 73. The file types are equally depressing. We have 1 database file, 2 JSON files, 15 Python files, and 5 YAML configuration files. Configuration files like config, example, YAML dictate where the actual data lives, pointing to directories such as data overlord, DB for the database path, and data events, JSON for event logging. The system relies on structured models such as overlord state, which tracks player stats like progress level, deaths, favor, and chaos. The state snapshot function pulls these variables together, including the player's name, current progress level, and accumulated deaths. These tables specify the mobs involved, the effects applied, and even a maximum mob count for each severity tier. Reward structures are similarly defined in configured tables. YAML outlining items and flavor text corresponding to basic, mid, high, and legendary tiers. Let's pivot to language distribution, because apparently this whole operation isn't written in a single cohesive dialect. The sheer volume of code suggests a reliance on 2 primary languages for this mess. Specifically, the metrics show that Python dominates the code base with 2062 lines of code. JavaScript trails behind, clocking in at 173 lines. This disparity is expected when dealing with systems that seem to have been patched together rather than architected. Looking at the file types, we see a standard collection of configuration artifacts. There is 1 database file, 1 example file, and a single instance of an INI file present. The JSON variants are slightly more common, with 1 standard JSON file and 2 JSON files logged. We also have a handful of markdown files, text files, and tags scattered around. The YAML configuration files make up the bulk of the structural definitions, accounting for 5 distinct files in total. So to summarize, a heavy reliance on Python, a moderate presence of JavaScript, and a configuration structure built primarily on YAML. It's not elegant, but it is functional. Let's look at when this whole mess was touched. The file modification times span a rather specific window. The documented history shows modifications occurring between 2026 016 04 54 17 plus 0 and 2026 06 to 71 thin 39 15 plus 0. That's the entire scope of iteration we have. A span of about 2 weeks, which is generous if you rare counting how long it took to decide what to name the next configuration file. It suggests a period where things were actively being hammered together, rather than just sitting there waiting for someone to finish the job. This timeline confirms that this directory has seen significant activity over that period. Now we turn our attention to the core event processing pipeline, which dictates how incoming data actually gets handled. The initial trigger often comes from the bot layer, where specific in-game occurrences are translated into external communications. For instance, when a bot detects a spawn event, it constructs an event payload and attempts to send it out via the post-event function. This function handles the HTTP request, ensuring that whatever data is sent is wrapped in a JSON body and transmitted to the specified API URL. Once an event is generated, it enters the system via the in-process event bus. This bus maintains a dictionary of subscribers, allowing various modules to listen for and react to events without creating unnecessary surface area. The system relies on state models, such as Overlord state, to aggregate all relevant metrics before any decision is made. When a new event arrives, the Minimax client uses this state snapshot to construct a detailed user prompt for the LLM. This prompt incorporates everything from player history and recent events to current scores like favor and chaos. The prompt also explicitly lists the allowed action types, which are strictly enforced by a validator. The LLM then generates a raw plan based on this input, which is subsequently extracted into a structured JSON object. This plan is then validated against rules defined in models, ensuring that the output adheres to the expected structure. The core of any intelligent director is its memory, and here we have a model dedicated to tracking everything. This state is encapsulated within the Overlord state model. It tracks fundamental metrics such as the player's identity, their current progress level, and various scores like deaths, favor, and chaos. The state also maintains a list of active goals that the director is currently focused on, alongside recent events and the last plan executed. When generating a plan, the snapshot is fed into the Minimax client. The client constructs a history summary by pulling data from the state, including player deaths and progress level. It also aggregates recent events, summarizing them by event type and the Minecraft day they occurred on. Furthermore, it includes notes from memory and the titles of active goals to provide context for the LLM. This compiled information forms the player history summary that is injected into the prompt template. The system then uses this entire package, the event, the state snapshot, and the allowed actions, to construct a detailed user prompt for the LLM. The core of this system is encapsulated within the goal spec model, which defines what a goal actually is. This specification includes fields like a title, description, creation, and expiration days, and placeholders for completion rules or reward plans. When a new goal is instantiated via create goal, it generates a unique ID, ensuring the format adheres to a specific regex pattern. The function enforces basic sanity checks. The title and description must not be empty, and the expiration day cannot precede the creation day. Upon creation, the goal is persisted by calling memory upsert goal, which handles the storage. The system provides endpoints for querying these goals, allowing retrieval of all active goals or filtering by status. If a goal is found by its ID, it can be retrieved using the get function. The process for marking a goal as finished is handled by the complete function. When completed, the status of the goal is immediately flipped to completed, and any provided memory note is appended to its record. This status change is then reflected in the database via memory upsert goal, and an additional memory note is added to track the completion event. The API exposes a dedicated endpoint, goal complete, which calls the tracker's completion logic and returns the updated goal data. The core of this system is encapsulated within the goal spec model, which defines what a goal actually is. This specification includes fields like a title, description, creation and expiration days, and placeholders for completion rules or reward plans. When a new goal is instantiated via the create goal function, it generates a unique ID using a UUID format. The function enforces basic sanity checks, ensuring that the title and description are not empty, and that the expiration day is not before the creation day. The endpoint calls the tracker's completion logic, and raises a for her if the goal ID is not found. The fundamental tracking of player progression is encapsulated within the Overlord state model. This state object explicitly maintains a field for the player's current progress level, defaulting to 1 if not specified. This metric is crucial because it feeds directly into the decision-making process. When generating a plan, this snapshot is passed to the Minimax client for processing. The Minimax client incorporates the progress level when constructing the user prompt for the LLM. Specifically, the template uses the progress level to set the context for the LLM. The prompt template injects the level directly into the system context, ensuring the AI has the necessary difficulty setting. Evidence suggests that this level is used to enforce per-level limits on actions and items via a validator. For instance, test data shows that a plan generated at level 1 includes the level field. This metric is crucial because it feeds directly into the decision-making process. When generating a plan, this snapshot is passed to the Minimax client for processing. Specifically, the template uses the progress level to set the context for the LLM. The prompt template injects the level directly into the system context, ensuring the AI has the necessary difficulty setting. Evidence suggests that this level is used to enforce per-level limits on actions and items via a validator. A sanitized plan, known as validated plan, contains an integer field for the level. This structure suggests that whatever comes out of the LLM is immediately clamped to the current difficulty level. How does the director decide what happens next? It's not magic. It's a carefully constructed prompt designed to force compliance. The core mechanism relies on the system prompt instructing the AI to choose one of 3 specific outcomes: punishment, reward, or challenge. This instruction is detailed within the event prompt template, which sets up the entire decision matrix for the LLM. The criteria dictate that a reward outcome should be chosen when the player has done something good, such as an advancement or surviving a hard moment. Conversely, a punishment is selected for recklessness, death, or ignoring a goal. If the player issues a challenge, the AI must use the action type setGoal to issue a new task. The raw output from the LLM is captured in an unplanned model before it undergoes sanitization. This raw plan is then passed through a validator to produce a validated plan, which includes the final clamped outcome type. The validation process ensures that whatever comes out of the LLM is immediately clamped to the current difficulty level via a field named level in the validated plan. This clamping mechanism suggests an attempt to keep the generated actions within defined boundaries, which is rather quaint. The entire process is designed to ensure the AI doesn't just spout nonsense. It has to adhere to a strict, predefined set of disciplinary actions. The core logic for interacting with the language model resides within the Minimax client class. This client is responsible for taking an event, a state snapshot, and allowed action types to generate a plan. When initializing, the client checks if an API key is present. If not, it defaults to using a built-in mock client. The process involves constructing a detailed user prompt by combining the event data with the state snapshot. This prompt incorporates player history, active goals, recent events, and current scores like favor and chaos. The prompt template injects the progress level directly into the system context, ensuring the AI has the necessary difficulty setting. The output format is strictly defined as a JSON object containing an overlord line, the outcome type, and a list of commands. The raw output from the LLM is captured in an unplanned model before it undergoes sanitization. This raw plan is then passed through a validator to produce a validated plan, which includes an integer field for the level. We now turn our attention to the actual prompt structure, which dictates how this whole operation talks to the language model. The system relies on a mechanism to load specific prompt files by name, whether or not they end in a txt extension. The core instruction set is housed within the event prompt template, txt file. This template establishes a rigid structure, starting with the current state of the game world. It injects variables such as the progress level, Minecraft day, and player statistics directly into the context. The prompt also includes a summary of the player's history, pulling from recent events and memory notes. Crucially, it lists the allowed actions whitelist, specifying exactly which action types the AI is permitted to use. The decision criteria section then forces the model into one of three predefined outcomes: reward, punishment, or challenge. This structure dictates that a reward outcome is chosen when the player has performed something positive, such as an advancement. If the player issues a challenge, the model is instructed to use the action type setGoal to issue a new task. Finally, the template mandates a strict JSON output format for the model's response, ensuring compliance through enforced structure. The raw plan generated by the LLM is captured in an unplanned model, which we explicitly state we do not trust until it passes validation. This raw plan is then passed through a validator to produce a validated plan, which is the only thing we actually care about. The resulting structure, defined by the validated plan model, includes fields like overlord line outcome type and a list of commands. The validation process is designed to ensure that whatever comes out of the LLM adheres to a strict set of rules. The validator first checks if the overlord line is present and non-empty, raising an error otherwise. It also checks that the outcome type is one of the three permitted states: punishment, reward, or challenge. The system is particularly keen on blocking specific command strings. For instance, any string starting with a / is forbidden within a command dictionary. If the LLM attempts to use an action type that isn't whitelisted, it gets rejected. Specific commands are subjected to granular checks based on the current difficulty level. For example, when validating a spawn mobs command at level 1, the validator ensures the mob count does not exceed 3 and that the distance from the player is within 20 units. Similarly, when applying an effect like levitation at level 1, the validator clamps parameters such as effect duration and amplifier to define maximums. How this whole configuration system manages itself. It appears to be a collection of YAML files that someone decided were necessary. The core function for loading everything is loadAll, which caches the results for the lifetime of the process. This function attempts to locate the configuration path, checking an environment variable first, and falling back to a default file if the path doesn't exist. If that primary path fails, it defaults to using config example, YAML, which is always a comforting sign of abandoned setup. The resulting dictionary contains the main config, alongside separate files for advancement levels, allowed actions, reward tables, and punishment tables. We also have separate functions dedicated to pulling specific pieces of data, such as player settings and server runtime parameters. The server settings, like the host port and whether it's a dry run, are gathered by merging information from the main configuration with environment variables. Meanwhile, storage settings are handled separately. They determine where the database, event logs, and plan files will actually reside. These storage settings explicitly define paths for the data directory, log directory, and specific files like Overlord, DB, and events. The system ensures that these directories are created if they don't exist, which is standard practice for software that clearly hasn't been properly deployed. The LLM settings are pulled from the configuration, defaulting to specific URLs and model names if those details are missing. In short, the system loads a sprawling set of YAML files to define everything from server ports to where the inevitable mess will be stored. Let's examine the reward definitions. It seems this whole system relies on a collection of YAML files that someone decided were necessary. This loading mechanism pulls in separate files dedicated to reward tables, punishment tables, and advancement levels. Specifically, the function getRewardTables retrieves the reward data by calling loadAll and returning the reward tables entry. The actual reward structures are defined across several tables, including basic, mid, high, and legendary. Each table specifies a list of items that can be awarded, along with a count range defining how many items are given and a flavor describing the accompanying text. The director then uses this data to determine what reward pool to present based on the current level. If the level is low, it selects the basic pool. For levels up to 5, it defaults to mid, and higher tiers trigger high or legendary. This logic pulls the items, count ranges, and flavor descriptions from the corresponding table to construct the final reward list. The core mechanism for retrieving these tables is encapsulated in getPunishmentTables, which pulls the data directly from the results of loading all configuration files. This function achieves this by calling loadAll and then extracting the punishment tables entry from the resulting dictionary. The raw data is sourced from punishment tables YAML, which defines the structure for different severity levels. The configuration file defines 4 distinct categories: weak, moderate, severe, and legendary. Each severity level specifies which mobs and effects are applicable, along with a maximum mob count. For instance, the weak table lists zombies and skeletons as mobs, allows slowness and hunger effects, and sets a max mob count of 3. The system also includes flavor text for each outcome, which seems to be the only thing keeping these tables from being pure, unadulterated data dumps. When the director needs to select a specific punishment pool based on severity, it calls punishment pool for severity. This function attempts to retrieve the requested severity key from the punishment tables. If that specific key doesn't exist, it defaults to using the weak table. This fallback mechanism suggests a reliance on the weakest configuration if something goes wrong, which is typical for poorly managed systems. The structure of these tables clearly shows an attempt to categorize consequences, even if the implementation feels like someone just dumped lists into a YAML file.